So topic for today, the first half of the session is regression, and let me start with the concept of correlation. And this is the mathematical concept of correlation, which is essentially about the relationship between variables. And in our case, we are looking at two variables. So we can look at what you call the scatter plot that can be used to decide whether there exists a correlation between two variables, ideally, because it's easy to visualize. So you may have come across, and this is a topic that you've already covered in your math courses, which is Introduction to the Mathematical Foundations of Machine Learning and Data Analytics. So when you plot two variables, so for example, in our case, x and y, and you may see that as x increases, y tend to decrease. That's one context that you can see. Other can be like x and y tend to increase at the same time, and you can have a scenario where there is a non-linear relationship between the way in which x and y moves, and there can be a context where you don't see any relationship. Right? These are the four contexts that you can see when you look at the correlation between a pair of variables, say x and y. And this is being shown using an appropriate plot over here. It's for two-dimensional context where there are only two variables. This is pretty evident. And if you want to quantify the extent of relationship between those two variables, you can go for fine-grained representations such as a correlation coefficient, which I'm not representing out here. So all I want to say is, if there are relationships between variables, correlation is an interesting mathematical concept which can represent that relationship. That's all I wanted to say, right? And the relationship can be, as you already see in this picture, it can be what you call the variables can have a negative correlation or a positive correlation, or they can be uncorrelated, or non-linear correlation can exist. And once you see that there is a relationship between these two variables which are under consideration, what can you primarily infer from that relationship? Right? Is it the first thing that comes to your mind? Is it just coincidental? Is it an accidental relationship, or is there a real relationship existing between these two variables? Right? And the primary one that you can think through is a cause-effect relationship. Essentially, a causal relationship. So, for example, the age of your car will right? If you're looking at x as the age of your car, and y is a amount that you spend on its maintenance, you can say, like, as the age goes up, age of the car can cause what you call the cost of maintenance shooting up, right? So age can cause what you call can affect essentially the cost of maintenance, right? Or is it just a cause-effect relationship? Is x causing y, y causing x, or is what you observe is essentially is just what you call a coincidence, or are there complicated relationship? X and y are connected, but y cannot decide x, or x cannot decide y. Rather, there are other variables. Say zi's along with x can potentially decide y. So, for example, relationship, is it more of what you call a complicated functional relationship? The simplest one being, say, for example, you can think of BMI, right? Body mass index, which is being decided by your height and weight. So, is there a more complicated relationship existing? So, these are the questions that you can ask. So, what is regression? All right, what is regression? Is essentially, it's all about can you model that relationship? Is there a way in which I can represent that relationship that exists between two variables? And what are the basic types of relationship that you will see between variables? Let's take the example of two variables. It can be, as we already seen, it can be as simple as a cause and effect relationship, or it can be more complicated functional relationship. I've given you the example for what you call the BMI, right? It's nothing to do with cause-effect relationship. It can be a more complicated what you call functional relationship between variables, right? If you say that if y is essentially decided by x, then you call y the dependent variable in the context of regression, and x is called the independent variable or explanatory variable. People call it predictor variable, and y is called the predicted variable, right? So x is independent predictor or explanatory, which can essentially decide or predict y, or it can be the what you call y can be the response of x, and it can also be called the dependent variable, right? So this is between two variables. So what is regression? Regression is essentially the mathematical notion of representing the relationship, the functional relationship that do exist between one or more variables, right? Currently today we are going to look at the relationship that exists between, to start with, the relationship that exists between two variables. Say, for example, x deciding y, right? Is there a way to represent that relationship mathematically? And you have seen a very limited, restricted context of this kind, which is x being a description and y being a class, right? We call that classification. So the moment we have a lot of xi, yi pairs, where x is the description of the data and y is a positive +1 or -1, a two-class context, you call that a binary classification problem. Can y be a real number? That's the question that we are currently asking. You have a lot of training examples which are represented as xi yi pairs. That's your training data, where xi is some r-dimensional vector, and basically d-dimensional vector in the real space, and y is a real number, right? So if that's the case, how do you go about doing it? How do you go about mathematically representing such a relationship? And we are going to see only linear relationships today, right? Let me get into the math part of it. Examples of regression context. So the time needed to fill a soft drink vending machine will essentially depend on the number of bottles needed to fill the machine, right? If the volume, or you can even say like the volume of the capacity of the machine, right? And the maintenance cost of a car, this is something that I've already given you, the example that I've already given you. The age of the car will decide. So the dependent variable is the maintenance cost, and the independent variable will be the age of the car. The repair time of a computer will depend on how many parts to be changed, removed, replaced, whatever, right? In this case, we can say that the statement can be read as y is a function of x. And how do you mathematically represent this notion of y is a function of x, right? Is there a relationship? And if there is a relationship, is there a relationship that is mostly to do with the identifying the relationship? And correlation is a good example, good mathematical tool to identify such a relationship. If such a relationship do exist, right? How do you model such a relationship mathematically? And this is another example that I've taken from the public domain. An operations supervisor, basically who maintains the operations, measured how long it takes one of our drivers to put 1, 2, 3, and 4 case of soft drink in their soft drink vending machine. In this case, the level of explanatory variables is x can be read. The independent variable can take values 1, 2, 3, and 4, and she controls them, right? How much to put can be decided, and she might repeat the measurement a couple of times at each level of x, and the scatter plot of the resulting data might look like this. So these are the points that she has plotted, right? How much time you typically take to load that into the machine, right? Number of cases versus the time needed to load that case. I mean, basically the bottles with case is essentially a case of bottles, right? How much time it takes, and you can see that you can essentially represent, and the line was not there. So what you can do is you can essentially represent such a relationship, possibly by approximating that to a line. You can say like the relationship to some extent. I can say that okay, the relationship that exists between the independent variable number of cases and the dependent variable loading time is more of a linear relationship, and you can see that it's not true here, but that's one way of looking at it. So another example, the relationship that exists between a dependent variable and an independent variable, because we are considering the simplest among the cases. A farm operations student is interested in the relationship between the maintenance cost and the age of farm tractors, right? The one that they use to plow the land or other agriculture later work, and he performs a telephonic interview of 52 commercial potato growers in a city, basically FL, and one of the one part of the questionnaire provides information on tractor age and Yeah, and basically like and another is like there's a typo there, and the maintenance cost, right? Maintenance cost will involve what do you call the cost of fuel, lubricants, repairs, etc. So you get a single variable capturing the amount to be paid to be spent to maintain, and they plotted it. So tractor age versus maintenance cost, and you can see that the relationship is like unlike the earlier case. This relationship is not linear; it's more of a non-linear whatever, right? And you see some interesting shape out here. All right. So this is another example, right? The question that asks is like, okay, the relationship can be as simple as linear, can be non-linear. Let us look at the simplest among the relationship. What is the association between y and x? Y is the independent variable and x is the y is the dependent variable and x is the independent variable. How can change in y be explained by changes in x? What are the functional relationship that exists between y and x? That's question and can be mathematically modeled. And regression gives you the answer. Right? Regression tells you how do you mathematically model the relationship that exists between dependent variables and independent variables, if such a relationship do exist. All right? How do you check for the existence of such a relationship? It can be the mathematical tools such as correlation coefficient will give you insights into it, right? Or a scatter plot can give you the say that there is a relationship and how do you model it. Right, a function relationship. So, for example, y is a function of x. Right, x is the independent variable and y is the dependent variable. Right, and we are looking at the case where both are univariate, meaning I have a single variable called x and I have another variable called y. Y is the dependent variable and x is independent variable. So, and the simplest among that would be, let's assume that the relationship is linear. Y is mx or b1x, right? Y is mx or y is b1x or beta 1x. So where b1 or beta 1 or m, whatever, the way you represent it becomes the slope of the line. And we are considering a line which is passing through the origin. So the y-intercept is also 0, right? Y is equal to mx is the simplest among the relationship. All right. If we know that if the relationship is more of linear, how do you model that relationship? Is what our topic today. All right. So example is, I told you the example, the simplest among the relationship can be a linear relationship. Y is equal to b0 plus b1x or b1x plus b0. b0 is a y-intercept and b1 is a slope. All right. And you can stare at this picture, which is essentially like, like dy by dx would be that'll be the slope, right? b1 and you can see b0 is essentially where does that line touch the y-axis. So this is something that must be pretty evident to you, right? So the simplest among the relationship is linear. If there is a linear relationship that exists between x and y, how do you model it? Is the question that we are going to ask today. All right, and you can have more complicated relationships. For example, the relationship can be a polynomial relationship, right? So you see a polynomial relationship out here between the variable x and the variable y, and so y can be the crop yield, x can be the pH value of the soil in which you are actually cultivating, right? It can be a complicated relationship further down, right? It can be non-linear relationship that we have already seen in the case of soft drink vending machine, right? So relationship doesn't have to be a linear always, but we are looking at the context where the relationship is assumed to be linear. Concerns, right? So we need to mathematically model that relationship, and let's assume that the relationship is linear. The proposed functional relationship will not fit exactly. That's one context that you need to consider, right? We have decided that okay, let's model this relationship. So there are primarily two aspects that you need to be worried about when you have decided to model this relationship. The first aspect is where do you get this data? You have a lot of samples taken from the context in which you need to model, right? Which you call as in the classification context, we call that training set. You can also call that in the regression context your training set. So you've got a lot of values sampled from the potential domain of values that x can take. So we have a lot of xi's and the corresponding yi's. So we have got xi yi pairs, xi being your data, and yi being the value associated with y. So essentially you have xi yi pairs. Now you must have realized that you're classification is essentially a restricted form of what you call. You can view that as a restricted form of a regression, right? Where the values are limited to be plus and minus. In the case of binary, values are limited to be 1 to n in the case of an n-class classification problem or a multi-class classification problem. All right. So in our case, in the regression context, you have xi yi pairs, x being univariate here, so it's a value. In the general context, x is a d-dimensional real vector. Let's assume that, and y is a real number, right? Y is a real number. Xi, yi, you have m such training points. So when you want to model, right, you're trying to model the relationship that exists between x and y using an appropriate mathematical model, and you have samples, you have got training data. Two things can happen here. You may not have the right data. There can be errors in measurement. That's one context. All right. The other thing is you don't have you don't have a proper model. The model is inadequate to model to represent your context. Right, the error can be in the model, error can be the specification of the model, right? So what happens is when you try to look at this equation, when you try to model, the relationship that exists between x and y using a functional relationship which is f of x gives you y, there'll always be an error. This is in the context of regression. This is called a residual error. This is called a residual error. This is a term that you need to be conversant with. The possibility of errors in the proposed relationship is always there, and it can arise either due to an error in measurement when you take samples through which you model the relationship, or it can even be f is inadequate to represent the relationship. There will always be an error. Epsilon is a small random variable representing the result of both errors. Right? It can be a specification error or it can be a measurement error. Whatever be the case. So this is a general form of a regression modeling, right? Basically, the mathematical the modeling context that a regression represents, right? So the relationship between y and x is represented as y is a function of x plus when you have f approximating the relationship between y and x. There'll always be an error due to error in specification or due to measurement, and that you represent using a random variable called epsilon, which is essentially called a residual, right? So regression analysis. What is regression analysis? Let's go to the simplest among the relationship, which is a straight line, a conservative starting point. Regression analysis is the process of fitting a line to the data, because we are assuming that our relationship is a linear relationship. In the two-dimensional space, it's a line, and the n-dimensional space, this is a hyperplane, right? Fitting a hyperplane to the context, basically, right? That's what it is, right? It dates back to Sir Francis Galton introduced this concept in 1822 to 1911. Is a British anthropologist, and the term is coined by him. Regression, right? So a simple regression model. Another example, we'll see more concrete examples today. A company that repairs small computers needs to develop a better way of providing customers typical repair process needs. To begin the process, they computed data on repair times and the number of components need to repair or replacement from the previous week, and data is sorted, right? So you have all these INX number of components. So for these 14 examples, you have these XIs, basically the components needed, and based on that, they wanted to give an estimate of how much time they would typically require to whatever. All right, that required time in minutes. So this is an example for a relationship. So you have data of this kind. That's what all I want to convey from this slide is you have xi, yi pairs where xi is some value and yi is another value. Xi is that we presume that xi is the independent variable and yi is a dependent variable, right? Yi can yi be predicted in terms of xi values with some approximation error. Right? That's the question that we are asking today. And the relationship is assumed to be linear. Right? Let's get into the mathematical formulation. So we had enough of textual material out there. So the relationship can be yi is, let's assume that the variables are beta is, yi is, and we presume that's a two-dimensional context. and relationship is assumed to be linear. So yi is beta 0 plus beta 1 xi plus epsilon I. So epsilon I is the error that you make while trying to predict yi, the value yi, using the value of xi, and the corresponding what you call model variables are beta 1 and beta 0, and the error that you make in that context is epsilon I, and that's, you have got n such examples. So estimating the regression parameters in the case of a line, the regression parameters, as you know, that it's essentially the beta 1 and beta 0 parameters here, which are essentially the slope of the line and the y-intercept, right? How do you model the parameters of a line? Objective, all right? What are you trying to do? You want to estimate. You have got a lot of samples, like, see, these are the samples xi by a phase, and you've got a lot of data. Right? So you have got a lot of data like this, computer repair time and the number of variables, and you plotted it here. So, and you see that the relationship is more of linear. How do you fit in this line? What is your agenda? You want to get the best fit, right, with respect to your data. That's your agenda, and you know that there is an error. What is your agenda? You want to minimize these errors such that you get the best line, right? Objective is to minimize the difference between the observed and it's predicted according to the line, all right? That's the agenda. So you want to find that line which best fits into my data, all right? That's the agenda. So the objective function is minimize the notion of error. So what is error? Error in representing. So this is a functional relationship that you have presumed. You have presumed that this is a linear relationship, and that's what we are looking at today. We have the model, what do you call, the structure of the model is presumed. We want to essentially predict the parameters of this model, right? The parameters of this model, and the model is assumed to be linear, which means that you have to predict. Essentially, you have to decide the parameters of beta 1 and beta 0 representing the line, right? So that the epsilon I, the error that you make, is minimized. So the error that you make, your objective function, so essentially the problem that you're trying to do is get me that line which best fit into my data, right? Get me that hyperplane which best fit into my data. That's the problem statement. That's objective that you define for a linear regression model. Get me that hyperplane which best fit into my data. Right? Objective is to minimize the difference. Objective is to minimize the difference between the observation and its predictions according to the line or the hyperplane in the n-dimensional space. In our case, we are looking at only at the two-dimensional space. So hence the name, hence the word line. Right? Otherwise, you use a generic context, linear context in the n-dimensional space. Use a hyperplane instead of a line. Right? So you have the notion of error. Error is, you know that. If this is the model, and once you have estimated these parameters, this model can be used for any given xi for which you don't have the corresponding yi. You can actually estimate yi, right? And you call that yi cap, the prediction, right? What this model gives out is represented as yi cap. So the error will be like the actual yi from your training data. You know the actual yi. You know the expected value of y. And you have the model given value, right? What will be the model given value? So the expected value by minus the model given will be the error. What is the model given thing? The model is this, right? Beta 0 minus beta 1 xi, right? That's what it is. So epsilon I is essentially yi minus beta 0 beta 1 xi. And where y bar represents the predicted value of y, right? Y for x is equal to xi. Right. So what is our agenda? We want to find that line or that hyperplane which best represent my points. Right. This is done by finding beta 0 and beta 1, which minimizes the sum of errors. Right. When you represent, so here comes the notion of error. How do you represent the error function? Right. You can represent the error function in multiple ways. The simplest way is like I can always take the absolute value of that error and sum it up all the points. Right. The most practical context is sum of squared residuals. So this is called the residual. This is, I've already told you, this is called the residual. Epsilon I is also called the residual. Right. So the best representation, the best what do you call approach? I mean, the most popular approach is let us try to minimize. Let's define our objective function as the error is basically represent the sum of the squares of the residuals. Right, and my agenda is to minimize. My agenda is to find the values of beta 0 and beta 1 in such a way that the sum of squared residuals is minimized, right? Find me, get me those values of beta 1 and beta 0 such that this term, which is nothing but the sum of squared residuals, is minimized, right? And this approach is called the method of least squares. So, and this particular way of approaching this problem of linear regression is called least squares regression or least square estimation in regression, right? We want to find beta 0, estimate of beta 0 and beta 1. This is called the least square estimate of beta 0 and beta 1. I hope you must have found parallels with the earlier context. Do you remember gradient descent? Essentially, you are representing your error function and you want to do a descent over a gradient function with respect to your data. We have got available data, and your error function is E is equal to summation over I is equal to 1 to n EI epsilon I square. This is basically the square residuals, and so you want to minimize E, find beta 0 and beta 1 in such a way that E, the residual error, which is essentially represent the sum of squared residuals, is minimized, right? Get me those values of beta 0 and beta 1 which will minimize my error. Right? How do you do it? This is, you can see that this is a quadratic term, and essentially like you have got a sum of what you call epsilon I square, which is quadratic in nature. So we can do what you call straightforward. We can apply the first order necessary conditions in a gradient descent context. You can do a gradient descent over the error function. That's what is happening. So there are textbook which talks about this particular context as the gradient descent process also. I just wanted you to be, that's absolutely true, because it's essentially what we do here is gradient descent. All right, you have error, you want to find what you call beta 0 and beta 1, and your error is represented as, when you have a specific value for beta 0 and beta 1, you have the corresponding EIs, and you basically like square it up and add it up over all the training examples, and you have this stuff, right? How do you do a gradient descent over this particular context with available data? So you apply the first order necessary conditions. You must have seen this. You may remember that from the gradient descent discussion. You may remember it from likelihood discussion, right? Maximum likelihood estimation. So essentially, what you do is you are essentially searching for the best values of the parameters which will minimize my error, right? So what you do is you do dou E by dou beta 0 over this function. So because you have got two variables, dou E by dou beta 0, find me dou E by dou beta 0, and assign that to assume like assign that to 0. This is the first order necessary conditions for a minimum, right? And when you do it, you get what you call, see, this term into summation, this term into over beta 0, you get -1, and you get what you call, when you do beta 1, you get a term which is of the kind x transpose x inverse into x transpose y. So essentially, you get two expressions, and the expressions will look like this. Those who are interested, you can do the algebra there, and you get expressions of this kind. Our expression will be where sxxy and ssx will be like this. Essentially, you find basically, see, if xi's are your input data variables and x bar is your mean of x, right? You basically like you center with respect to the mean. The every data point you center with respect to the mean. You add it up over all the points, and then that's what sxx is. And what is this? You see this? Do you see anything related to the mathematics that you studied? So essentially, like you're essentially like multiplying. What is this? This is basically you're essentially looking at what you call how far each of these data point is from what you call how far each of these data point is from its mean. Right? You see parallels with your measures of what you call spread, right? So I don't want to call it. You have, I hope you have gone through a theory of what you call variance and covariance out there. So this is essentially like spread over a variable, and this is spread across variables. That's the way I want to represent this. Spread over the variable versus spread across the variable. So your slope will be like spread across the variables divided by spread over the variable. That will be the slope, and from that dou E by dou beta 0, you can see that beta what we call beta 0 cap, which is essentially estimate of beta 0, will be what we call it will be the mean of y minus beta 1 into mean of x. You can easily see that. I've already derived it. I don't want to share it because it's what do you call it? It's so simple. So you just do differentiation and you get it. And the only thing is you will see that you will see a slight mathematical variation from this expression, which is essentially like which says you have to center the variables with respect to the mean. So that's only a difference that you'll see when you do that algebra. Otherwise, it's straightforward, right? So you get this expression, and so once you have these expressions, you know everything, right? This is linear regression model, right? Let's look at an example, and which is find the equation of the regression line. You have got these are the values you have. You have x's and y's. This is just for your what you call convenience. I have put these values also. These are in the slide that I have taken. So the public domain data. So you have got xi, yi. Can you find the different? Can you find what you call a regression line that fits in this relationship, right? Can you mathematically represent the relationship that exists between y and x, and y is a dependent variable and x is an independent variable. So how do you get this? You can actually put all these columns because it's easy to compute. So what I want you to do is just go through this, what do you call it? Take a piece of paper, write down these expressions, right? Take a piece of paper and write down these expressions. The estimate of beta 1 and beta 0. Just write down these expressions and do that computation for that simple case. Then you will see like how do you actually do it. You've done that. Just let me know once you've done that. Beta 1 is equal to what you call spread across variables divided by spread across spread inside it. Basically in the context of a single variable. That's what it is. You know that. See this goes well with your understanding of your notion of mean, right? And beta is like this. So have you written that? Just let me know. I'll give you 2 minutes to take a piece of paper and start doing this. This is straightforward. There's nothing much complicated, but I wanted you to get that data field of regression. And I'll give you a little more complicated context to experiment with. Have you written that? Beta 0 is equal to. Okay. So this is what beta 0, and whereas x, you can write the expression. You can write this expression. If you want the complete thing, you can write this. Otherwise, you can write just this part. Basically, this can be like algebraically reduced to this form. So you take what you call the squares of xi and sum it over and 1 by n into this. Sxx is equal to this, and sxy is equal to this. Sxy is equal to this. Just copy that also. Sxx is equal to this, and sxy is equal to this. So you can just write this final part. If you want to do this, that's so fine. This is a little more easy to compute. Sxy is basically it's a measure of spread across variables. This is a measure of spread inside a variable. So that's what it is. Right. But you have run that, right? So just write that, these 2 expressions. So connect that to a notion of variance and covariance. It's easily understood, right? So good. Once you have that, just compute this. Compute beta 0 and beta 1 for this beta 0 cap and beta 1 cap for this particular data set. Where this is x, so this is an independent variable, and this is a dependent variable. Just compute what you call beta 0 and beta 1. I'll give you a minute, which is straightforward. So all you need is, you need to, if you have got these expressions, what you need is xi square. Xi square is xi square minus 1 by n into summation xi the whole square. That will give you sx. Sxy will be yeah, you add it up over this xi by a and do this. So I'm keeping this data. So everything is available here. And in your chart window, put the values for beta cap, beta 0 cap and beta 1 cap. Estimate of beta 1 and beta 0. What will be that line? Represent that line for this regression context. It's so simple, but I wanted you to basically, how do you fit in data to a line? So that's what I wanted you to understand. I mean, hands on. And I want you to go back, look at this slide today itself, because it's so simple. But this is a topic that people typically complicate. I want you to have this understanding before we get into what you call the log likelihood modeling, which is essentially like the logistic regression model, which is considered to be what you call discriminative model. Right? I wanted to give you that flavor. So what you have done in Bayesian context is typically called a generative model, and what you typically do with a logistic regression is called a discriminative model. So I wanted you to have that feeling, at least a pointer to that feeling. That's the reason why I give you enough of time so that you can refresh the basics of regression, and then we'll go maybe in the next class. Right? Have you done that? Have you computed beta 0 and beta 1 estimates, beta 0 cap and beta 1 cap? If you have done that, just put it in your chart window. Just put that values, beta 0 and beta 1. Right. Those who have not done that, do it. And make sure that you understand this. So essentially, you fit in your data. Right, you represent the mathematical relationship that exists between these two variables as a line, right? As a regression line. No, you're wrong, Vinayak. You don't get that sort of values. So I have done that. There's something wrong with your calculation. Just check your xxx and xxy values. I've done that. I've got the result also here. Your calculation is wrong. So xi, yi, just write these equations carefully, and you get this. I want at least one to get this. At least one person to get. You should get this. This is what it is. I've done that. I've done that yesterday. I have a piece of paper. This is basically like simple. Just you will get what do you call it? Beta 1 is equal to 1.2 and beta 0 is equal to minus 3.8. Beta 1 is equal to 1.2 and beta 0 is minus 3.8. This is basically it's pretty straightforward. So for example, if you add, if you basically you want a term, right? Sigma xi. What is sigma xi? If you add sigma xi, sigma not xi, sigma xi and sigma yi, right? What is sigma xi? It will be like 1 to 6. This is 15. Add it up to 15. This will add it up to. This will add up to what is the? It's not absolute value. It's actual value, right? This will add up to minus 1. Right. This term will be 1 by n, 1 by 5 into 15 into what is this term? This will be minus 1. Right. 1 by 5 into 15 into minus 1. So that will be that kind of xi, yi pairs. If you add it up, you have this, right? 14 plus minus 5. So you get 9 here, right? So you get 9 here. So this will be, so this term will be 9 minus 1 by 5 into, what will be this? 1 by 5 into, we have seen 15 into minus 1. That will be 9 minus 1 by 5 into, so you get that down there. So likewise you get 9 minus this thing, right? What will be the term? So 15 into minus 1, right? 15, 1 by, so 9, you get it, I think you get 9 plus 3, right? 9 plus 3 here. So you get 12 here. You get 12 here, and this will be 1 by xi square. What will be xi square? Xi square, you have it here. You add up these things. This is 14 plus 30, 30, right? This is 30. This is 30 plus 25. 55. You get 55 here. 55 minus 1 by into summation xi the whole square. So 55 minus summation xi, this is 225, right? 225 by 5. What will be that? So it will be around 45. So you get 10 here, right? You get 10 here. What was the number we got here? This is 10 here, and this is 12 here. This will be 12, and this will be 10. So 12 by, what will be beta x? 12 by 10. So you get 1.2 here. Beta 1 will be 1.2. This is what is y bar? You get, so y bar minus beta 1. This is 1.2, right? This is 1.2, and this is x bar, right? Let's look at 15 by 5. This is 3, right? What will be, this is y, this is minus 1 by 5, minus 0.2. So if you apply it here, y bar will be minus 0.2 minus 1.2 into 5. All right, 1.2 into 5 will be 1.2 into not 5. 15 by 5 will be 3, right? So you get minus 0.2 minus 1.2 into 3 minus 3.6. So 0.2 minus 3.6 will be minus 3.8. So that will be the thing. But these are the values that you get. Don't worry, and you will be able to, like, you can even look at this line. The line will look like this with this data. All right. So yes, it's minus 3.8. It will be minus 3.8. Yes, that's true. Kevin, that's right. So 19 once, slide number 19. Just go through this. It's straightforward, and I thought I'll just ask you to do it once so that you get your hands dirty. Don't worry, I have one more slide which tells you a more complicated context like this. A lot of data, and how do you fit in a line there? How do you fit in the regression line there? How do you estimate the parameters? So the whole point here is, I think, let's move on from this, right? Okay. Vinayak, just check it out. It's simple calculation, and you can easily, if you do it in school, right? But when you do it beyond that, it will become difficult. So I just want you to go through it. Jayant, you're right, 1.2 and minus 3.8. Good. So don't worry, I'm giving you a more complicated context. All right. Go look at this data and do the same exercise, and you can fit in the parameters. And my slide had the parameters also. I didn't want to. You just go find out and discuss among yourself and find out how do you fit in a regression line for this context. Right? The slides will be shared in immediately after class, so you can look at this also. I don't have the answer here. You discuss among yourself, and I have done that, but I don't want to share it. Good. So that's a linear regression model with the two variables. You have a univariate context. You have an x deciding y. If there are multiple variables, right? Let's multiple regression context. This is multiple regression context. You may have to do a prediction. You may have to do a prediction of a dependent variable using more than one independent or explanatory variables. For example, so Monday's test create from the previous session, might be considering the number of classes a student is taking, student's previous knowledge of the test material, maybe the number of hours spent on the study, etc., etc. So multiple regression equation will look more generic. So it'll look in a more generic fashion like this. You have what you call y bar being you have an intercept plus x1 and x2, maybe like up to xk. K variables are there, and k independent variables deciding a y. Right? This can be more complicated context. And the m's are the corresponding slope, right, with respect to y. And how do you estimate the parameters? You again represent y bar is equal to this plus epsilon, and you can do the squared residual. Sum of squared residuals becomes your error function, and you can minimize that error function. And once you minimize that error function, you will get a term. The term will be like, if your parameter estimates are m's or betas or whatever, that be equal to x transpose x, where x is basically the vector of x's, right? You have got the observations for x. So you have got x1, basically the first observation for x. So you'll have values for x1 to xk. So x, you can presume that, and you have the b also. If you remember your perceptron implementation, you have padded up with the 1, so that the y-intercept can also be taken care of. So basically, you have an X matrix where the rows represent the data, the X values, along with the pattern one, right, for capturing B. So you have got that X, and you have got, for each of these X values, basically like the X vector, there's a corresponding Y. So let's assume that you have got M X vectors and the corresponding M Y values. You have got an X matrix, you have got a Y vector, right? The X matrix will have, all right, since we assume that there are k variables in the context in which you are considering k independent variables, x's. So the X matrix will be k plus 1 in columns, and you have m rows, which means that you have got m training examples. So you have got k plus 1 will be the number of columns, and m will be the number of rows. So m by k plus 1 will be the dimensionality of x, and y will be, right, for each of the m x vectors, you will have the corresponding y's. So you will get y1 up to ym, right? That will be the predicted, basically the dependent variable. So if you do very similar, which is not there in your primary context, I don't want to use that today. If you do a similar gradient minimization procedure, if you do an error minimization procedure with the epsilon, the residual being introduced in this context, you will get an expression of the form very similar to the one that we have seen in the univariate context. The expression will be the parameters will be x transpose x inverse into x transpose y. That will be the form of the parameter vector. Right, that's what you're going to set. Your m1 up to mk will be m1 up to mk will be equal to x transpose x, right, inverse of that into x transpose y. That'll be the the expression that you get for m1 to mk, which is very similar to this one, right? If you look at that, your expression over here, this is essentially SXXY. So this is basically like it's centered around. So you can x transpose x inverse, right? That's what it is in univariate case. Then do x transpose y. That'll be the kind of form. X transpose x inverse into x transpose y. Y will be the vector. Yeah. So that'll be the kind of form that you get, and correspondingly you get this expression also. So basically, like your beta 0 parameter will be, you take the essentially the across all the observed variables, you take the mean and multiply this along with the mean of the vector. So you get so you know that. So this beta is not univariate anymore. In a multivariate case, it will be a a vector, and this will be another vector. You get transpose the parameter vector transpose the mean of the mean vector, mean of the input data vector. parameters. So that's what we are going to see in the case of multiple regression context, which is not, the mathematics is not discussed here, and probably maybe at a later point in time we may come back to this and look at that in detail if the maths looks interesting. So you get expressions of this form. That's what it is. So it's an example that I've taken again from the web. The following multiple regression equation can be, so it's a two variable context, x1 and x2 deciding y bar, the rice yield in US or whatever, and where x1 is a number of acres planted and x2 is a number of acres harvested in thousands, right? So basically the static service, some data is taken. Predict the annual yield x1 is equal to and x2 is equal to 2704. Predict the annual yield when x1 is equal to. So what you do is, once you have these parameters, you can put the values there, right? So the yield when these parameters x1 and x2, you just put it back. You just put it back, all right? Put it back to, you have these parameters estimated as I always said, x transpose x inverse into x transpose y. That's the way you do it, and you apply it back, and you get this expression. You get this value, right? That'll be the yield, and that'll be the yield for the other pair, right? For the next input. So, in essence, you can actually try it for a two variable context, and then it'll become. I've done it for a one variable context. You basically take this context of two variables, x1 and x2, predicting y, and try out the error minimization procedure, and you get that expression. Right? You write, what you do is you write the expression for E and try to find M1 and M2 in such a way that M1, M2 and B in such a way that the error is minimized. The first order condition is applied. So what you do is dou E by dou M1 and dou E by dou M2 and dou E by dou B is equal to, they are all equal to 0, and you get expressions for M1 and M2. So you get a very simple expression, and you can write that in a vectorial form. You will see that it will be of the form. So M1, M2, B will be equal to x transpose x inverse into x transpose y. That will be the standard form that you get. That's how you get. That's how you define, and primarily estimate the parameters of this model of the multiple regression context. So I want to stop the discussion on regression over here, and back to your question. Your what do you call the exercise that I gave for you to practice, example 2. It's a univariate context in the original case. See the B, use the equation to find the expected test score for a student who watches. So A part, you will estimate the parameters, beta 0 and beta 1, right? Using these X and Y scores, right? You have got, using this data, you find the parameters of the model, beta 0 and beta 1. Once you get those parameters, you can write the expression of the line, or the hyperplane in the n-dimensional context. You get this is a two-dimensional context, you get a line, equation of a line. Using in that, instead of x, if you put 9, you can do this. So you need to predict the test score of a student watching TV for 9 hours. So when x is 9, what will be y? That's what you need to do. Right? You have values also. So this is what you need to do. Go back, look at this, and learn this carefully. And we'll come back to this because we need to learn more complicated context than a linear regression model. And we can try with a two-variate context also, very similar equations and gradient descent or error minimization procedure. And then once you have, and do that this week itself, because next week probably we'll cover up the remaining topics in this regression bit, and I want to stop the discussion on regression over here, and we'll move on to the next topic later.